Oh, oh, ho, ho. Hello, everybody. Um, welcome to my channel. Happy Friday. Welcome to my channel. Um, I guess today I'm doing my live stream for December 17th, 2021, and we're just gonna do some TenderJIT hacking again today. But oh, hello. Let's first go to the presentation portion of my live stream. Yeah. So actually, where's my keynote? There we go. So we're just gonna do some hacking on TenderJIT today. But I want to I don't know, talk about some other stuff too. My camera angle is a little bit different. You may have noticed because I got a new desk. Oh, I'll talk about that in a second. Happy Friday! Wah! Happy Friday, everybody! Um, yes, so I got a new desk. So my camera angle is slightly different, and I'm still getting used to it. But it is a very nice desk. Unfortunately, it is just as messy as my previous desk, though. But what's nice is that you can't see it on the live stream. Also, yesterday was my birthday, and I had a good time. I didn't really go out or do anything that much, but we did set up like a photo booth. So Ebby and I took photos. Took photos at the photo booth. This is one of them. I also made a cake, and it's a chocolate cake. I was gonna make a red velvet cake, but I didn't have enough stuff, so I decided to just go with chocolate cake this time. And this is the inside of it, which is surprisingly still chocolate on the inside. Yes. I also over the past 2 weeks, so I'm trying to do this live stream at every other week, like cadence. And over the last 2 weeks, I've been working on some modifications to my food dehydrator. I'm trying to make black garlic. And in order to make black garlic, you have to basically keep garlic at a particular temperature for a very long time. You have to keep it at about, what is it, 130 degrees Fahrenheit, 53 degrees Celsius approximately. And I have a food dehydrator, which I like usually do that in. And like Ebby noticed that there was like a burning smell in the basement, and I took a look, and my food dehydrator was overheating. I measured the temperature, and I tried turning it down, but it just, I don't know, it just wasn't working very well, and then it burnt itself out. It has like a inside, it has a fuse, like a heat-based fuse. So if it gets too hot, then the fuse will just like blow, and then it'll shut itself down. So to prevent fires and stuff. Uh, but I wanted something that was a little bit more accurate than the current food dehydrator, so I fixed it, and I made this thing, which is basically a controller for the food dehydrator. So I 3D printed a new knob for it, which you can see there at the top, and I hooked a servo into that, and then it feeds into it's got a temperature sensor that I ran inside the food dehydrator, and then I guess I'm in the way here, but you can see it like right there is an ESP that I'm using for controlling the temperature. So basically, what it does is it just tests the temperature and then adjusts it to make sure that it's correct. Here's a close up of the 3D print, and since I have this hooked up to Wi-Fi, we can see the temperatures. So I'm logging all the temperature as well as all the temperatures as well as the angle that this servo is at. And I wanted to show, so this is what it looks like. Like I'm logging it into an InfluxDB and then graphing it with Grafana, and you can see here I'm doing pretty well at maintaining 53 degrees. But I want to show. Let's see. I'm gonna show you what it looks like now, because it's not. I don't know. I think there's something wrong, but I just want to be honest about it. Show everybody. So this is the graph of it here, and let me see if I can make this bigger. Does it get bigger if I do plus? Yeah, it does. Nice. Okay. So this is the graph, and you can see something's going wrong right here. I'm not sure, I'm not 100% sure what's going on. it went up to 80, which is absolutely not expected. So like if I do, let's go back and look at the past, I don't know, 24 hours of data. You can see like it's holding at 53 pretty well, but something happened this morning and I don't know what exactly. Um, if we look at like down here, this graph is a graph of the temperature. So this yellow line is a temperature and the green line is a servo angle. So it's like measuring how much around it's rotated the servo. We can see it's like mostly normal. It's bouncing up and down here between 0 and I guess 40 degrees or so. And then here it's like, whoa, brings it way down because the temperature is rising for some reason. Let's go back here to an hour. No, not an hour. We don't want to see that. Like it's now it's maintaining temp again, but something happened. Let's look 6 hours ago. Here we go. Yeah. Look at this. It pulled it all the way down to 0. The sensor was like, it's too hot, so it brought it down to 0, yet the temperature kept rising. So I'm not sure what it is. I suspect that this food dehydrator is just like totally broken because it kept logging these values and it definitely turned it down to 0. So I'm not sure why it did this. But anyway, let's go back to the presentation, which is here. Okay. So keynote, there we go. I'm going to do my next, so like I said, I was doing these every other week, but I think in 2 weeks is New Year's, so I'm not going to do it that day. I'll do my next stream on January 7th, so please everybody come join me then. All right, so I'm trying to do Robert's rules of business. So let's cover our old business first. So a couple weeks ago, we were looking at expand array, the expand array instruction, and the expand array instruction looks like this. Basically, we have like anytime you have like an x comma y or some kind of comma operand right here, we get an expand array instruction emitted. So Yarv will compile that into an expand array, and we all know that that's basically what that means is like. Oh, right. So we get an expand array. It takes the array and it pushes the array, like the array values onto the stack, which I think I have a slide for later. We also discussed object layout. So there's different types of arrays. So we have embedded arrays where the arrays are like the values of the array are stored inside of the object itself. And then we have another extended array where the values are stored inside of a malloc buffer. And my cat is snoring, so I'm going to try to get her to not snore. And we talked about how I had already implemented a case where like when expand array gets an array and the array is long enough to push all the values onto the stack. So we have X, Y, Z, like maybe, the array is long enough to support all those values. We had implemented that since last time. I implemented all of these cases. So the expand array instruction in TenderJIT now handles the case where the array is too short, or whether it's embedded or extended. So all of these cases it handles. But there's one other case that we didn't really talk about at all a couple weeks ago, and that's the case where like, what if the object that we're trying to call expand array on isn't actually an array? So let's say, for example, we have some code like this. It's just we have this OMG method and we're passing true into it. So this works. You can do this in Ruby. It's fine to do. And the return value will be this true and nil. So the expand array instruction will say, oh, okay, well, you're just expanding some value that's not an array. What we're going to do is we're going to take that and then just push that value onto the stack and then push nils onto the stack nils onto the stack as well. So the way I decided to tackle this, which I think is kind of interesting, and I wanted to discuss it in the live stream today, is I kind of implemented what I think of as like a new instruction. It's not a real Yarv instruction. It's just one that I made up just to help me kind of think about this situation. And I called it the Coerce Array instruction. And essentially what it does is, let's say like, our normal expand array instruction works something like this, where we say like, okay, we do a get local. The get local pushes the array onto the stack. Expand array then takes the elements out of the array and pushes those elements onto the stack. and then we do a set local with those values that are on the stack. So that's the normal array based case. If you pass in like true, sorry, I literally made these slides this morning, so they don't look super amazing. If you pass in true, we need to push a true and a nil onto the stack in that case. So what I decided to do is introduce this new instruction, which you can see here, like below the get local, there's this other one called Coerce Array, which isn't a real instruction. It's just something I made up. And what we'll do is we say, okay, well, we're going to do a get local, and get local will push true onto the stack. And Coerce Array, what it does is it pops the value off the stack, and it says like, oh, this isn't an array. So I'm going to make an array, and I'm going to push that array back onto the stack. And then expand array is going to pop that off and say, oh, I got an array. And it's going to say, well, it's too short, so I'll push nil onto the stack, and then I'll push true onto the stack. And the nice thing about this is that expand array only ever has to deal with arrays. It doesn't know about true or false or any other values. All it knows is I'm going to get an array off the stack. I got to figure out, is the array long enough or short enough, and then push enough values onto the stack. And we'll do the normal things. Oh, thank you for happy birthdays. So we'll do the normal thing where we just set the locals and pop the values off the stack. So it's exactly the same as before. So expand array, the point of this new instruction is that expand array only ever sees arrays. So I wanted to have the code as like, it just deals with arrays, and that's all we have to know about. But like I mentioned a little bit before, we take that true value and we have to allocate a new Ruby object, and we don't really want to do that because allocations will slow things down, and we just don't want to do more allocations. Now, oh, thank you. By the way, if any of you have questions, please just put them in the live chat. I'm happy to answer any questions that you have along the way if anything's confusing or anything. Anyway, we can think when we have a program, not just a Ruby program, but any program on our machine, there's essentially two places where it can allocate data. And this isn't specific to Ruby at all. This is just programs in general. There's two places where we can allocate data, and those are, the first one is a heap allocation, which you're probably familiar with. It's when you do like a malloc, any type of malloc or mmap, those kind of system calls. You're like, hey system, I need some memory, please give it to me. Now the other place that we can do allocations is on the stack. So we can say like, I need to allocate memory on the stack, and I'm gonna get into that in a little bit here. So the way stack allocations work is, let's say we have our memory. This box here is representing the entire memory on your system. Low addresses are where we typically deal with malloc information. So that's where all the all heap allocated stuff starts at the top at the low addresses. High addresses, so when we allocate via malloc or whatever, we're actually moving down. So we're moving to higher addresses. Stack allocations work from the opposite side, where we start at the high addresses, and when we want to allocate stuff on the stack, we actually get smaller. So we have to move the stack pointer up. So the way that we do allocations on the stack is via stack pointer manipulation. And that's specifically done with the RSP register on x86. And I'm going to show, I want to show a demo of that because I think it might help a little bit more if we see it actually in action. So let's do that. Go over here. So I'm going to go to the terminal. I'm going to pull up my ASM REPL. There we go. Yep. Oh, I can just do, I can do that. Can I do that? Will it work? I think I can do, no, come on. I think I can do touch. Apparently not. Okay, whatever. All right. So RSP is our stack pointer. So this is where we're pointing at in the stack right now. And there's different instructions that'll manipulate the stack pointer. So Etienne is asking, what about toArray? We will get into that. I will show you when we get into the code. So where was I? All right, RSP points at the stack, so that's the stack, the stack pointer. And whenever we do, like, let's say we do a push operation, we can say like question. Rodolfo is asking, what are your thoughts on JEmalloc? That was a life changer when I added it to my Ruby in production here. Yes, I love JEmalloc. You should definitely be using JEmalloc in production. Just do it. Just do it. All right. So RSP is our stack pointer, and this is where the stack is pointing in memory, and we can manipulate this stack pointer. So let's say, for example, we use we're going to do it first with a push instruction. So let's say we write a value to R9. Let's write the value, I don't know, 10. All right. So register R9 changed. We wrote the value A. I guess A is 10 in hex. So we put the value 10 into R9. Now, we can use the push instruction in x86 to take that value, whatever that value is, it's going to write that value into the stack. It's going to push it onto the stack. So we can say push R9. And when we do that, you'll see RSP changes. Our stack pointer changed. What happened was it took the value that was in R9 and wrote it into stack memory, and it had to change RSP when it did that. So you can see it changed by 8 here. We were at C18 and now we're at C10, and we actually got smaller. So as I was showing in the diagram, we're growing up. We're going from large addresses and we're going to smaller addresses. So now we can say like, oh, let's put the value, I don't know, OXFF in R9. So we do that, and you can see it changed to OXFF. RSP didn't change, but we can do this. We can say like pop R9, and what'll happen is it's going to read that value off of the stack and put it into the R9 register. So we'll do that, and now we see, oh, okay, RSP changed. We added to RSP because we deallocated some stack memory, and then we changed the value OXFF into A. So what's kind of interesting about this is we can manipulate the RSP register not just via push and pop. We don't have to do push and pop operations necessarily. We can say like, let's just do sub RSP. I don't know, 40 seems like a good number. So if we do that, we can see that the RSP register changed locations, and all the memory that's between BF0 and C18, it's unused. And we can actually write anything we want to into that memory. So I'm not going to do it right now because I haven't practiced this. I'll probably mess it up. But we can write stuff into this memory right here and use it for whatever we want to. But what's really cool about this is we didn't have to do any system calls in order to allocate memory. We just subtracted from RSP, and now we have some space in memory that we can use for whatever we want to. Now the catch is that later on we have to subtract from, or we have to add back to RSP in order to deallocate that stack memory. So this is how we can manipulate the stack and use memory in the stack without having to call malloc. So get back in here. Let's go back to Keynote. So what we can do is we can say, okay, well, the coerce array instruction, what it can do is it can say, well, okay, we push a true onto the stack, so we see a true. The coerce allocation sees the true on the stack, and it's like, oh, this thing isn't an array. I need to make an array. So what it does is it says, okay, well, I'm going to subtract from RSP, and I'm going to write out some memory here that looks like an array. So it looks like a Ruby array. It has the same layout as a Ruby array, but it didn't have to allocate it out of the GC. It just looks like an array, and then it's going to push an array onto the Ruby stack. So this thing looks like an array, and it contains the value true, but we didn't actually allocate it out of Ruby's garbage collector. And in this case, we're going to use the embedded version. So we'll say like we want an embedded array. We're going to make the first we just have to make sure that the class pointer points at array. We have to make sure that the first element inside the array is true. And then we can fill in the other two slots with q nil if we want to. So in this case, I know in the slides it looked like we're allocating a one element array of q true, but actually I just decided to do a 3 element array with true and then 2 nils in it. Now let's take a look at what's up next. Yes, it quacks like an array. Let's take a look at the actual code, because I think that's pretty interesting. It gets to Etienne's question about toArray, which I think is fun. Let's see, where are we? Oh, thank you. Merry Christmas to you too. TenderJIT. Let's see. Is this font big enough? Should I bump? No, let's bump it up. Let's bump it up. It's always nice when it's easy to read. Let's see. I see compiler. Okay. So, not coerce array. Let's look at this. So here's our normal handler for expand array. Like this is the handler we use for expand array. It takes a num and a flag, and we talked about that before. And what I did was I just said, okay, well, let's also call handle coerce array. So we're going to pretend that there's always, before the expand array instruction, there's always a coerce array instruction. If we go look at that, what it does is we take a pointer to this function rbCheckArray type. And what this thing does, this is fun. CheckArray type will call, like, it'll check to see whether or not you can coerce something into an array or not. And let's actually go look at that function. Do this. And then what was the function again? CheckArray type, tag rbCheckArray, no, CheckArray. Is it array? Yeah, there we go. Okay, so what it does is it takes a value, which may be an array, and it tries to call toArray on it, toArray. And it also checks to see whether or not it's a T-array. If it can convert it into an array, it returns the converted array. Otherwise, it'll just return, well, q nil, I think. So what we do is, this coerce array thing, it says, okay, well, if the thing on the stack is a special constant, then we'll try calling this array, this toArray type. If that returns something, then yeah, we're gonna push the return value, this right here, the return value onto the stack. If it didn't, then we're gonna call this compile push array onto the stack. So we'll try to convert it. If we can't convert it, then we'll do this thing. Now we have another case here where, like, so this thing checks whether or not it's a heap allocated object, a Ruby heap allocated object, not a machine heap allocated object. If it's a special constant, then we go through this dance. If it's not a special constant, we'll check the type and we'll say, hey, if this is an array, if this thing is an array, we just won't do anything. We'll do nothing. Because we know it's an array, we just want to leave it alone. Otherwise, we say, like, oh, let's call that function, and again, exactly the same thing as the special const situation, but down here with a heap allocated object, we'll say, hey, we'll call this. If it's nil, then we're going to do our special thing. If it's not nil, then we're going to push that return value onto the stack. But regardless of whatever branch we go through in this instruction, the thing that ends up on top of the stack is an array. It's always an array. So let's take a look at compile push array for a second. This is where all of the awful magic happens. What we do is we say, like, okay, we're going to take the RSP register, and we're going to subtract from the RSP register the size of a Ruby object. So we'll say, hey, I want to allocate 40 bytes. I'm going to subtract 40 from RSP. And it's not actually 40, and I'll get into why that is in a second. So we'll subtract some amount from the stack, and then we're going to keep the address of the stack. So we're going to figure out, like, what address it is. Then we're going to add a value, which is just for alignment. Rodolfo is asking, where do you check if you can indeed subtract? The RSP register always contains some integer value. It'll always have some number in it, and we can always subtract from it. If we can't subtract, we'll get a seg fault or whatever. The thing will crash. That means we ran out of stack space, basically, which I don't care. Get a bigger stack. I don't know. So we try to subtract from RSP, we add to temp, and then we start writing out to memory the layout of a Ruby object. And we say, hey, let's set the flags on it. We're going to say that this thing is of length 3. It's an array that's length 3. We're going to write whatever value it was we popped off the stack. So if we popped true off the stack, we're going to write that in as the first value of the array. And then we're going to fill out the rest of the array with q nils. I know I said in the slides it was just a 1-element array, but I decided not to do that. It's always a 3-element array in this case. It's whatever the value was plus 2 nils afterwards. So we write that in, and this comment, believe it or not, is not accurate. It says make it look like an integer so the GC won't try to mark it, which isn't true, because the thing is, like, we have this thing that looks like an array. Like, it looks like a Ruby array. And if anybody else gets a pointer to it or gets this value, like if anything else in the Ruby, like in Ruby sees this thing, it's going to crash because it's not really a Ruby array. We can't totally use it that way. We just made it look like one. So I incremented the value to tag it as an integer. So we'll push it onto the stack and it'll look like it's an integer, but it's in fact a Ruby array layout. All right. So let's see, right here, we don't actually subtract 40 from the value from RSP. So I think a couple weeks ago, we talked about how Ruby objects are always 40 bytes. And I'm actually allocating more than 40 bytes on the stack, and that's because we have to make sure that the stack has a particular alignment. So the stack value always has to be a multiple, on OS X it has to be a multiple of 16. And if we want to make sure that this value is always a multiple of 16, we can't always use 40. So I changed it to 48. So we allocate a little bit more each time, but it's okay because we'll just subtract the 48, or we'll add the 48 when we're done allocating. The other nice thing about tagging this thing when we push it onto the stack is when we're done with the expand array instruction, we have to say like, oh, we need to add back to the stack because we have to do this bookkeeping. Every time we subtract from RSP, we have to add back to RSP. Otherwise, we essentially have a memory leak. It's just that this memory leak is leaking on the stack rather than leaking in the heap, which kind of like, when I first thought about that, it kind of blew my mind. It's like, usually you're used to tracking down, well, I'm used to tracking down memory leaks in, heap allocated stuff. You're like, who's doing malloc? Who's doing malloc? But in fact, you can have memory leaks on the stack too, and that's probably like, I don't even know how you would track that down, to be honest. All right, let's see, back to the presentation. There we go. So this thing quacks like an array. It looks like an array, and we can use it as an array, but we just have to make very, very sure that nobody else sees this. And nobody else will see it because immediately right after we push this fake array onto the stack, we process it and then pop it off, and it goes away. All right, so let's move on to new business. This week we're going to do the top n instruction. And this is the documentation from the top n instruction. It takes the nth stack value from the stack top and pushes that onto the stack. So let's say we have a stack layout that looks like this. We have 3 values that have been pushed onto the stack. The top n1, if we have like top n1, all it does is it looks at the the 1th element, and then grabs that and pushes that value onto the stack. So it'll take bar and push bar onto the stack like that. Okay. Not thanks everyone. I'm not done yet. We're actually going to do it. Okay. So let's go do that. First thing we need is a test, of course, and I think somebody has already written a test for this. So let's take a look at that. Test instruction. Where am I? Oh, I'm in the wrong directory. Neat. Top n test. Okay. Yeah, we have a top end test here. And to be honest, like I'm not sure what this thing uses it for. It's like this is the code that uses it, which is some odd code. But I guess it uses it sometimes. The other thing is like I'm not sure where we got this test. Like I'm not sure how we figured out to use this code as a test case. But like if we run so let's say we run opt_carrot. So the reason I wanted to tackle this particular instruction is because if we run opt_carrot with TenderJIT, we'll see that it runs, and our top exit instruction is the top end instruction. So we need to fix this instruction so that we can move on further and do more JIT more code in opt_carrot. So that's why I wanted to target this particular one. Okay, so we have this test, and it currently asserts that we have one exit, and we don't want that. We want 0 exits. We're not going to exit from the JIT in the top end case. Okay, so let's do it. Def handle top end, and let's split screen with. The font's pretty big, so let's see if this looks okay. Yeah, I guess it's okay. So here's the top end. Here's the top end instruction. It takes one parameter, which is n, like the number, the nth, the thing that we're gonna look at in the stack. So we'll have like n here. And then all it does is it just grabs that value and then pushes it back onto the stack. That's it. So I think we can do that fairly easily. We'll do with runtime do RT, and this with runtime, what this thing is I kind of wrote a little DSL to do stuff. I know that's super descriptive. I wanted to separate compile time stuff and runtime stuff. So when we're entering into this handler, it's currently compile time, right? And if we look at actually I'm going to move this function down a little bit. So for example, we see these rt.if. That's a runtime if statement. So it's actually generating the machine code for doing this if statement. And you'll see like these kind of weird else's. It's because it's also generating the else branch for it too. So actually, when the compiler runs, all of this code gets evaluated. But what it does is it generates machine code that does this same thing. So this runtime object thing is essentially a DSL for generating machine code, and I think it's a little bit more expressive than like put label, jump label, stuff like that. At least that's the point of it. The other point is like I hope that we can start refactoring this into some kind of like IR. Okay. So top end, we got that. What do we do? So we want to do rt.push. We're going to push something. Let's do this. Runtime. Okay, runtime def push. What does push take? I forget what it takes. It takes a name, a value, a name, and a type. So we're gonna push, and it's gonna be actually let's peek at the stack. So we'll do peek equals temp stack dot peek n. So that's the value we're going to push. So we'll push the location, and the name is gonna be whatever we have in the stack name or in the temporary stack, and then we'll do type is also whatever we had in the temporary stack. I think this will work. I don't know. It did work, but also I'm a very bad TDD person because I didn't watch it fail first. So let's comment this out. Well, let's just delete it. Okay, it did fail. What is a failure? Expected 0, actual 1. Yeah, so test, here's our test on line 47. And this is 47, yeah. So we expected 0 exits and we got 1. Or no, yeah, expected 0, got 1. So let's add our function back, handle top n. And if we run again, we're good. Yay! Yay! We did it. Okay, so top n is done. Let's commit this. Actually, let's check out a branch first. $17. What did we do? Implement top n instruction. Okay, great. So let's figure out. That was very fast. We still have 24 minutes left. Let's figure out what to run next. So we did that. Let's run opt_carrot again and see what breaks. I'm sure something will break. Rodolfo is asking, do you need to use a DSL helper if there's an n, if n is already the top item? I guess you need to because of machine code. No, probably not. I think like if n is the top item, we could do, it would just be a dupe, I think. Because the top item is going to be like this thing, this instruction. That's a good question. This handle top n instruction doesn't pop anything from the stack. So it only ever pushes something onto the stack. So if n was 0, if this was 0 for some reason, we'd still have to push something onto the stack, but it would just be the top thing of the stack, which we actually already have an instruction for. That's handle dupe. Oh, handle dupe. Like, it's exactly, oh wow. It's like basically the same thing. Def handle, what was that? Top n. Oh, that's funny. So we could actually change this to be like handle top n 0. Nice. Thank you. Let's see if this works. Yeah, it totally works. Great. Great. Okay. What was I gonna do? Oh, let's commit this. This is awesome. Let's see. Refactor dupe to call top n with 0. So duping the top of the stack is the same as top n just with a 0 index. It's exactly the same. Nice. Nice. Yeah. Yes, please come join us. Okay, so we got that. That's very nice. All right, let's do, what was I gonna do? Oh yeah, opt_carrot. Let's see, opt_carrot. Run it, and it crashes. It crashes on compile opt aref with a not implemented error. So let's go take a look at that. I see compiler line 817. All right. Oh, I keep doing FG. I don't know why I keep doing FG. I think it's like the font being so big throws me off. So I'm like, 817. Raise not implemented error. Sure enough, there's a raise right here. This is, what function is this? This is compile opt aref. Ah, okay. So this is a case like, let's go look at the test for this. Test instructions opt aref test. So aref it's this thing. It's like when you just do an array reference, So like that. Actually, let's just test.rb. So let's do this. OMG takes A and B. We'll do A, B. I know this is like really weird code to write. You would never write this for real, but it's just to show what this looks like. So if we look at this, if we dump the instructions, there we go. So these are the instructions for the OMG method. Right here is OMG, and then you can see we're doing a get local on A. That's this A, and then we do a get local on B, and then we do an opt aref, and that's this call right here. And it looks like we're doing some specialization at runtime in our current opt aref. So we were saying like, oh, if it's a hash, like the way that we do a hash access is different than the way that we do an array access. So it's like, oh, if it's an array, we're gonna do this thing. If it's a hash, we're gonna do this other thing. But here we added an else statement that's like, if this is something else, like let's just raise an exception and then figure out what that is and then write a test for it and then keep iterating on our code. So let's check out what this thing actually is. It's not an array, it's not a hash. Let's just do p class. And I'm just gonna do like a hard exit here so that we can see the class and like just do something with it, like maybe write a test that's not opt-caret. So we'll do this, run it again. Okay, and the class is a method. So that's interesting. Keep doing that, FG, come on. So you could do like, it's really weird for somebody to write this, but you can do like something like this. Let's do like def hello, and it takes X, and then let's just have it like return X. We can do like method hello, and you can call it like this. This is a syntax for calling it. So you can be like hello, and then do like OMG, and it'll call that hello method. So you can use square braces on a method object. Again, I did it. I should alias FG to be like, don't do that, Aaron. All right, so let's write a test that uses a method object. It's really interesting. Okay, test instructions opt aref test. So we actually have an aref here. We have an aref method. Let's do like def test aref with method. I don't know. Let's write a method, def method, what's a good method name? Thing. So it's gonna take one value because key is gonna get passed as a parameter. It's gonna take one parameter, so param, and what we'll do is we'll say like, I'm just gonna copy some stuff. We'll just copy this method, and we'll say expected equals, oh, actually, let's pull out the method object. So m equals method thing, expected equals aref m comma something. So this is going to return the string something, so that'll be in expected. And then we'll compile aref and we'll enable it. And let's do down here, we'll do actual. We'll call it again while the JIT is enabled, and then do our assertion. So this is wrong. Should be expected actual. Okay. All right, let's run this. So hopefully we'll run this test, and then hopefully we'll see it exit in the same way that opt-caret exited, and then we can start doing implementation. The cat is meowing at me. Sorry. Get in your basket. There you go. Yes. Say hi to everybody, Choo Choo. Meow. Yes, okay. She doesn't care that I'm on a live stream. She's like, whatever. Pay attention to me, not your computer. All right, let's run the tests. Let's run just that one test. be ruby -i lib test instructions. There we go. Opt aref test. Oh, we got to make sure verbose is set. We have a really nice thing in our test suite that's like, if it produces any warnings, so if you have any warnings in your code, it just flunks the whole thing, which I really like. But you have to have -v enabled to do that. So we'll do that. There we go. Nice. There's our method. Let's run just the one test. Test aref with method. Like that. Okay, cool. We got that going. Yes, cat pair programming. Okay, so we got the method, we got that test case, and now we have to do something with it. I guess we have to call a method? I don't know. Let's actually just see what the normal interpreter does. Git opt aref. Okay, so VM opt aref, let's take a look. It checks like, okay, is this an array with an integer? Or no, this is like, is it a special constant? We'll have to write a test case for this eventually. If it's I guess you can do, you can do 1, 2. Oh my goodness. I know what this is for. Yeah. This is like, you can use array syntax on an integer, and I believe it returns the bits that are enabled at that index. So like, let's do an example. Let's do oxff. So this is going to be all ones for, what is that? I don't know, some number. I can't do math right now. Let's do, so 0, this is going to give us a 1. Yes, oh my gosh. So let's do E. That's a 0. Oh my gosh. Oh my gosh. 1. 2. Yeah, okay. I'm sure you're going to use this in all of your programming applications because you need to make sure what is a bit. Okay. If it's an array, then we do a thing. If it's a hash, then we do a thing. Otherwise, we do qundef. So this thing has special cases for integers. Well, I guess technically it's for like true as well, too, isn't it? True is a special constant. What does that do? What does that do? True? 0? Weird. Okay. All right, whatever. It's an error. All right. So it has 3 special cases. Otherwise, it just does a method call. So we should probably just do a method call. We'll just do the same thing. We'll just do the same thing that the interpreter does. How do we do that? How do we do that? Let's look at compile send. Actually, what's interesting is this opt aref, it takes a call data parameter, and this call data parameter is actually an inline cache, which is interesting. So this thing knows, like, this thing has an inline cache, so it's ready if you're gonna do a normal method call rather than one of these special case optimized method calls. It actually keeps a cache that information. So, okay. Can we just call compile send? So this is the case where we're just doing a normal method call. I guess let's try that. Like, compile send? Is that gonna work? Like, there's no way it's gonna work because nothing ever works the first time. We have CFP rec patch lock. Okay, CFP IQ patch location. Actually, no, I don't want to do compile send. We want to do the simple case, the very, very simplest case, which is no, I don't want to do any of this stuff. Let's just try it. Let's just try this case and see if it works. It does not work. It crashes. Okay, let's see. Let's see, what is the crash? Oh, gotta run it. Okay, run. What do we see in here? Fiddle pointer A set. We got an exec bad access at address OX5B. So, ooh, that's interesting. P offset. Offset's just some value. P X offset. Oh, that doesn't look good. That doesn't look good at all. Let's see. Let's see. Data pointer. What is this? P data pointer. Okay, I mean that might be legit, but this offset is like not good. Okay, let's just do BT15. Nope, too big. BT5. Call cfunc with frame. Doing that. Pointer.c. So we're doing, in some place we're using fiddle and we're passing the wrong value in. Like it's a very not good value. Let's take a look at our code. Compile send comes in through here. Blah, blah, blah. Oh, I wonder if it's this thing. It could be this thing. Let's do, so in order to debug this, oh, Rodolfo is asking, is that a fancy GDB? No, it is LLDB, which I guess is a fancy GDB, but in some ways it's not as fancy as GDB. It's less fancy than GDB, I think. Let's put, so I don't know where this is happening. So what I'm going to do is I'm going to add, like, I know this is like kind of a crappy way to debug this, but what I'm going to do is I'm just going to start adding exits, like exit bang, and then see if we can exit before the thing crashes. Let's run it. Okay. Okay, so it's not there. Let's try, like, I don't know, here? Okay, so we know it's not that stuff. Is it... Actually, you know what? Let's cut out even more. Maybe it's not even this function. Let's do here. Let's just exit right after that. Okay, so it's definitely in compile send. Let's try here. Okay. Fiddle unwrap. That seems okay. I'm not seeing anything too weird yet. It could be in one of these. Yeah, it's definitely in one of these. So compile send has specializations for each type of method that we call into. So if we're calling into a C function, we come in here and it generates specialized machine code for calling into a C function versus an iseq versus a B method. I'm going to guess that this one's a cfunc. I don't know for sure, but it's a square brace on a method, which sounds like a C. It's probably implemented in C and not implemented in Ruby. So let's do like puts LOLOL. Make sure we actually got into this case. Yep. Okay. So it's definitely a C function. What did we do wrong? Okay. I mean, this doesn't seem like too handling a C function doesn't seem like too much jazz. Let's try here. Okay. C func peak. Maybe here? What? Wow, okay, so it's not actually the compile C func that's breaking. Let's exit here. Okay, so we get past that. It has to be this patch source jump. What is this? Yeah, okay. So what is the issue? Let's look at this p method entry adder to s 16. Let's also print out the patch location. Oh, yeah, that doesn't look good. Okay. So what is the issue? That was the second one, patch location. So patch location is wrong. So we're trying to, like, the way this thing works is we insert these jump instructions into the x86 machine code, and we have to patch those jump instructions to go jump into the new method that we want to execute. So we're going to generate a bunch of new machine code, and we have to say the origin jump needs to jump into the new stuff that we generated. And so we keep track of a location that's like, this is the place that we want to patch. Like, this is the thing we want to patch. And for some reason here, our patch location is negative, which it absolutely should not be. We're not patching at a negative location in memory. So where is this coming from? Let's see. We got it up here. So we're trying to compute an offset, a relative offset. So JIT buffer.memory is the beginning of the JIT buffer, and we need to compute a relative offset from there into the location. Yeah, it overflow became because it became negative. I don't think that's what we're seeing in LLDB. Like if we look in here, let's actually go back. Where's our exit? So if we let it crash, let's let it crash. Right, we let it crash, and we can see here's our negative number. And then if we take a look at this offset number, p offset, we can see, yeah, we got ourselves that number right there. Okay. So why is this thing negative? Actually, I only have 2 minutes left. So let's stop here. I'm gonna keep hacking on this, and then try to get it fixed for January. But I just want to say thanks everybody for coming. I really appreciate it. I like having folks sit along and pair with me. So I will see you all next year. Thank you, everybody. Bye.